Our next example, we are going to look at the electrical circuits, and the questions say, given the electrical network shown below, find a state space representation if the output is the voltage. So the output will be the voltage across the capacitor. So it will be this voltage here. With electrical circuits, the state variables that we have to choose should be energy storage systems. So we are going to store energy in the inductor, and we store energy also in the capacitor. So in the inductor, the energy is stored as current, and in the capacitor it will be as voltage. So what we are going to choose is, we are going to choose our state variable as IL and VC. So now I'm going to approach this example in two ways. The first part, I'm going to derive it the way we've done in our earlier examples, whereby we changed our variables. Then in the next part, the second technique, I'm just going to solve it directly, so that you will appreciate both techniques and why you would prefer one over the other. So let's say that let's take VC is equal to X1. This implies that if VC our state variable, then the derivative of our state variable is equal to VC dot is equal to X1 dot. Our second state variable is IL, which is equal to X2. This implies that IL dot is equal to X2 dot. From the circuit, we can see we have our current that is going through here, and our current IL is here, and a current IC here. And we can see that IL and IC is the same. So we can say that IL is equal to IC, and we know the equation of IC is C dVc dt. So we know what IL is. So this, we can rewrite this equation as, we say IL is X2. So X2 is equal to C. So the dVc dt is our X1 dot. X1 dot. Okay? This implies that we can find our X1 dot. So X1 dot is equal to 1 over C X2. So the first state variable, it's done, the first part of the equation. The next part of the equation, we need to solve this equation. We need to solve this circuit using our KVL. And what we have is, from KVL, we have our input voltage is equal to the voltage across the resistor, and I'm going to use IL, because if you use IR will not be, it's not part of our state equation. So, and we know that IR, your IR here is equal to IL because it's the same current. And what we want, our states, we want IL, which is X2, and the VC. So I'll use IL plus L DIL dt plus VC. And I can change our variable. Our input voltage is equal to R. We say IL is X2. So I can just put x2 here plus L di dt. So the derivative of the current is x2 dot. So x2 dot plus and Vc was x1 plus x1. Now from there, all we need is just to, I can rewrite this equation. Just take this, rewrite it in terms of Lx x2 dot. So we can have Lx2 dot is equal to our input voltage minus Rx2 minus x1. Then we can solve this. X2 dot is equal to 1 over L, our input voltage, minus Rx2 minus x1. Now we have our equations. We have this equation, and we have also this equation, and we can write that in the form of our state equation, our standard form. So we are going to rewrite that. X1 dot we have, x2 dot we have, is equal to our A matrix, let me make it as big as possible, times our state variables, which were x1, x2, plus our input, which was our input voltage. Now we need to fill in this. X1 dot, from the beginning, we know that x1 dot is equal to 1 over C x2. So, no, x1 dot, yes, x1 dot is equal to that. So at x1 there is a 0, and here we have 1 over C. X2 dot will be 1 over Lx1. So here we have minus 1 over L times x1, this part and that part, minus 1 over minus R over L times x2. So we have minus R over L times x2. And we have also our input voltage, which will be at x1 is 0, and here we have 1 over L. And we were asked the output voltage. It says that the output voltage across the capacitor should be our output. Okay? So our output is Y is equal to something, and our state variable is x1, x2. And from the equation, we said our output voltage, we want the voltage across the capacitor. This is our Vc. And we say that Vc is equal to x1. So, meaning that from here, Vc is x1, and x2 you have 0. So, as you can see, this is now in standard form. It's straightforward. For equations that are not complicated, this method is straightforward. Let me use another method solving the same equation. Let me use another example or another method to solve the same equation. We can say that we chose our energy storage as our state, IL and Vc. And we can say that from the circuit, we know that IR, So the current across the resistor is equal to the current across the inductor, which is equal to the current across the capacitor, which is equal to C dVc dt. And from here, we can, because we want IL, all right? So if I say IL is equal to C dVc dt, and we can find our dVc as, this implies that we have IL over C is equal to dVc dt. And this is the format that we want. We can also write this, I'm going to write this in red, as 1 over C times our state variable, that what we want, is equal to Vc dot. That part is done. And we know that the voltage across the inductor is VL is equal to L dI dIL dt. This implies that your dIL dt is equal to 1 over L times VL. Now, we are going to use our Ketchups voltage law. Again, from KVL, we have our input voltage is equal to voltage across the resistor times the current, which is the same current that is going in through the inductor and the capacitor, plus L dIL dt plus Vc. We can rewrite this as input voltage is equal to R times IL plus VL plus Vc. Now, we can solve this equation, and the reason I want to solve it, I want to write it in the form of the VL so that I can substitute that VL into this, because I found already the di dt. So if we do that, we are going to have input voltage minus R IL minus Vc is equal to VL. Now I can put this equation in there. Then we have dIL dt is equal to 1 over L times our input voltage minus R IL minus Vc, okay? And I can rewrite, let me rewrite this, all right? So we have IL dot is equal to 1 over L times the input voltage minus R over L times our state variable in the inductor minus 1 over L times a state variable in the capacitor. So from here I can rewrite the equations in terms of our state space matrix, because what we have our first derivative in the current, and we also have, where is our Vc? We found our Vc here. So we are going to rewrite this. Vc dot and IL dot is equal to, our state variables will be Vc and IL plus something, which is our input voltage. I'll just put VIT there. And what we had for Vc earlier, we had this information across 1 over C times IL. So For VC we had nothing, but for IL we had 1 over C. And the next one is for VC is, we are looking at this equation, IL dot. IL dot we had, for VC we had minus 1 over L, and at IL we had minus R over L. And for our output voltage we had just a 0 here and 1 over L. Okay, so the output voltage is VC. Since we want the output, Y is equal to VC, and we are just going to write this Y is equal to something times VC IL. So we want the output to be VC, we just put the 1 there and 0. If you wanted the output to be the inductor current, we could have written this as 0 and 1, and you put your VC there and your IL there, but that's not what we want.